So today and over the next few lectures, we're going to be trying to prove the regularity lemma. So just to remind ourselves what that is. So G is a graph. We've got some parameters epsilon and t. And what I want to find is a partition of a partition x1 up to xk of the vertex set of G. So such that three conditions hold. So the first condition is that the number of parts, so k here corresponds to the k here. So the number of parts, we want it to be at least t, where t is our parameter from the beginning. And at most, some function k naught that depends on epsilon and t. So when I write k naught and then I write epsilon t in parentheses, what I mean here is that k naught depends on epsilon and t. And the important thing here is that it doesn't depend on G. So all I'm doing here is restating the regularity lemma, right? We've seen this before, but that was last week. So, and it's important to get this statement straight. The second condition is that practically all of the pairs xi, xj are epsilon regular. So with an exception of at most, like let's say epsilon k squared pairs. So practically all the pairs are epsilon regular. And the third condition is that all the sets have basically the same size. So they're all equal to either the floor or the ceiling of the number of vertices over k. So in some sense, the kind of way of proving this is not going to be that surprising in some sense. It's the actual way that we come up with this partitioning is not going to, it's going to be kind of straightforward. The difficulty is going to come in analyzing the method for doing it or analyzing the algorithm. So here's a little description of basically the first few parts of the algorithm. So I've got my graph G. I'm just going to start by taking a completely arbitrary partition into t sets of roughly equal size, where t is my parameter in the, t is this lower bound on the number of parts that I want to hold at the end. So if I want to make sure there's at least t parts, I might as well just start by partitioning into t parts. And then maybe the number of parts will increase, but if the number of parts increases, that's okay because it'll be at least t. And when I say roughly equal size here, what I mean is all the parts have size v of g over t or ceiling. Okay, so in this first step, there's nothing intelligent, right? Just take the vertices and however you want, just split them up into t sets. Obviously, if you got really lucky, you could say, at this point you should check, does it already satisfy the second condition, right? So the second condition says that practically all of the pairs xi, xj are epsilon regular. If somehow you got lucky and your arbitrary partition satisfied 2, so 2 is, this thing here, then you just stop because you've already, this arbitrary partition already satisfies the conditions. So that's kind of a silly case to consider, but you may as well stop if it already satisfies the conditions. Okay, so now we assume that the second condition fails, which means that I've got, in my arbitrary partition, I've got a lot of pairs which are not epsilon regular. If you haven't gotten lucky, then you know that 2 fails, condition 2. So there's a lot of pairs that are not epsilon regular. So now you have to do something to kind of improve your partitioning. So let's kind of look at an example, maybe not a specific example, but a sort of picture anyway. So let's suppose, for example, t is 3, right? So what we did was we started with an arbitrary partition into x1, x2, and x3, each of size about n over 3. Now suppose that the pair x1, x2 is not, so this pair here is not epsilon regular. Right, so this gives us, so what does it mean to be epsilon regular? Remember, so it means that if x1, x2 is epsilon regular, means that, so this is just restating the definition, for all a subset of x1, b subset of x2, such that the size of a is at least epsilon x1, the size of b is at least epsilon x2. The difference between the densities, so density from a to b minus density from x1 to x2 is less or equal to epsilon, where maybe I'll remind you that this density thing is equal to the number of edges from a to b over size of A, size of B. It's just the percentage of possible edges that there are between A and B. Yeah, totally. So, right. So if it's not epsilon regular, you kind of negate this statement, and therefore there must exist some subset of here and some subset of here, which are big enough, but the density between them is bad. It deviates from the density between x1, x2 by a significant amount. Okay, so kind of my picture looks like this. So I'm going to say there's a set A1, 2. So the 1 and the 2 here are supposed to correspond to the fact that we're looking between the pair x1, x2. The 1 comes first because I'm taking a subset of x1. So that's my explaining the notation. So anyway, there's a set A1, 2 here, right? And B1, B2, 1 here. The between them is too low or too high. It is okay that, yeah, so it's okay for some pairs to not be epsilon regular. But all I'm asking is, like, suppose this pair isn't epsilon regular, and what does it give us? But yeah, the number that can be non-epsilon regular is like epsilon times the number of parts squared, which if epsilon's small, then even having a bad pair might be a bad thing when you have only 3 parts. So, okay, so what we know is that if I look between these sets, the density between them is either, it's kind of, like Goldilocks, right? You've got like the porridge is too hot, too cold, or just right, right? Between A1, 2 and A2, 1, the density is too cold or too hot, right? The density is too low or too high. If a pair is epsilon regular, then between every pair of sets, the density is just right if they're big enough. Okay, so what it gives us, you've got these sets with this property, with these properties. Okay, so so now imagine that, like, you had more non-regular pairs. So suppose that, if let's say x1, x3 was also non-regular. So as was mentioned in the chat, like, we're not always going to assume that all the pairs are non-regular, because we could stop if only a few of them. But anyway, let's think about what happens if this pair is also not regular. And this kind of blending of colors didn't work as well as I thought. But okay, so suppose that the pair x1, x3 is also non-regular. What it gives you is a set here, which is this blue set, and this purple set where the density is too low or too high. And this blue set I'll call A13, and I'll call this one A31. Now, if you think about that, this if I look at x1 and I look at this pair of non-regular certificates, or yeah, whatever you want to call them, this actually splits up x1 into 4 parts, right? You've got the yellow set, which is, so this part, which is fully yellow, which is A12 minus A13. You've got the fully blue set, which is A13 minus A12. You've got their intersection, A12 intersect A13, and then you have the complement of both of them. So it's all the stuff that's in neither of them, which is the white region, which is x1 minus the union of A12, A13. Okay, so if the set x1 is involved in 2 non-regular pairs, it kind of gives us a way of splitting up x1 into 4 sets. Okay, so here's how the algorithm for finding a regularity partition works. So you just do an arbitrary partition into t sets, where here we're thinking of t as 3. You look for your non-regular pairs, and if a set is involved in a certain number of non-regular pairs, it causes that set to be broken up into a sort of Venn diagram of sets. You can see this is kind of a Venn diagram, right? These 2 non-regular pairs caused x1 to be broken into 4 parts. If it was involved in 3 non-regular pairs, that would cause it to be broken up into 8 parts, and so on and so forth. And all we're going to do is, I look at this part x1, it's involved in a lot of non-regular pairs, and I just refine the partition so that the parts are all the kind of segments of that Venn diagram, right? So you don't necessarily know that they're non-empty, and so non-emptiness is not such a problem, but smallness can be a problem. For example, maybe the set labeled 3 could have just like 1 element. I mean, it could also have 0 elements, and that seems like a problem, but you could just throw that out. But if it has 1 element, that seems like a problem, because I want all my parts to have the same size. But anyway, we'll work out how to fix that problem later. But kind of the initial step of the algorithm is to just arbitrarily use the non-regular pairs to split up every part in a sort of using the segments of the Venn diagram. Is it clear what I mean by this Venn diagram thing? And then there's going to be, then there's going to be another step after that to kind of balance the parts afterwards, which is important. And that's where this thing about, that's kind of related to this empty segment issue. Okay, so like in theory, maybe all three of, because I just broke it up arbitrarily into 3 parts, so maybe all 3 of them have non-regular, like maybe all the pairs are non-regular, which would mean I just take all of my 3 parts, each of them becomes 4 parts individually. So, right, so you split it up using the kind of Venn diagram thing, and so these 3 parts become 12, right? Each part becomes 4 parts, right? 1, 2, 3, and then the complement. And okay, and then kind of addressing the question from the chat, you then have to take these, so each of these parts and kind of monkey around with their sizes, move things around if they're too small, and do some things to mess with them. But essentially, this is the idea. Like, as long as you have a lot of non-epsilon regular pairs, all you do is you take the sets which certify non-epsilon regularity. Those things kind of break up your set into a bunch of pieces, and then you just take those pieces as the next sets of your partition, and then you have to monkey around to make them the same size. But let's not worry about that too much. And you basically recurse this over and over and over until finally your pairs are almost all, I should say. So all but, so when I say almost all here, I mean all but epsilon k squared of them, where k is the final number of parts, are all epsilon regular. So is the kind of algorithm, apart from the part where I say that you have to make the parts the same size, which we won't really talk about until the end. But is the algorithm clear? So it's really kind of straightforward, I think. I mean, the part that's not straightforward is how on earth do you analyze this? And maybe the definition of it is not completely straightforward either, but okay. Right, so just out of curiosity, like, it's interesting to think about how many parts you actually get from this. The numbers here get scary. Like, these are not numbers that we normally see in combinatorics. So like, okay, suppose step 0, we had 3 parts. So, and this is kind of related to what was in the chat. So in step 1, you have at most 12 parts because every set got broken into 4 parts at most. Now suppose we refine again here. Now if I look at, let's say, so now I've got x1 up to x12, let's say. How many parts does x1, like, so in the maximum, like at most, how many parts does x1 get broken into? I think it gets broken into a lot more than that, because potentially it could have a bad thing with x1. It could have a bad thing, or sorry, with x2. It could have a bad thing with x3 all the way up to x12. And that's going to be a very complicated Venn diagram. I would say it's even more than 16. So basically every kind of, I don't know, for every, so the relationship of x1 and x2 breaks x1 into 2 parts, right? And then every part could get broken up into 2 parts by looking at x3. Yeah, so I think we've got it. Yeah. So 2 answers there were close to the 12 and 2 to the 11, and 2 to the 11 is correct. Yeah. So just the part x1 gets broken up into potentially 2 to the 11 pieces, because basically if I look at the non-epsilon regular thing here, like, you can think of this set as breaking x1 into 2 sets, that set plus the complement. This one breaks, if I look at the non-epsilon regular thing here, it could break this one, the set involving x2 into 2 parts and the complement into 2 parts. And basically, so that makes 4. 4 was what we had last time, right? And then we keep doing this and it breaks it into 2 to the 11 parts. So, and every part could have been broken into 2 to the 11 parts. So we have 12 times 2 to the 11 parts. And the way this kind of goes is that, like, if you look at f of k, where the f of k is the upper bound on the number of parts at the kth step, it's then let's say we look at the k plus first step, it's at most, I think, f of k times 2 to the f of k minus 1 because I had that many parts and each of them could be broken into that many pieces. So it's like recursively applying exponentiation. So you have, 3 and then you have 3 times 2 to the, to the 3 minus 1. But anyway, it's recursively applying exponentiation. So like in particular, this is going to be at least, this number you get here is going to be more than 2 to the f of k, right? This is a simpler function to deal with. So if I take, it's going to be something like 2 to the 2 to the 2 to the 2 to the, if you take k steps, you've got at least, or you could potentially have a tower of 2's of length k parts in the worst case. So this is something they call a tower function. So, tower, so this is, I guess, the notation, I think. Tower of k is the function defined as like, it's 1 if k is 0, and otherwise it's 2 to the tower of k minus 1. So I'm only defining integers here. So like the number of parts you could get is something like a tower if you do this for k steps. Okay, so these are numbers which are ridiculous, but that's what you get, and that kind of explains. So we have these applications of the regularity lemma in the previous few lectures, and I kept kind of vaguely mentioning that the dependencies on the parameters are terrible, in the sense that as some parameter goes to 0, the other one goes to 0 ridiculously fast and stuff like that, and that's coming from this tower dependency, essentially, or if you say invert this tower function or something like that. Now, here's a really big issue. Like, yes, I can tell you this algorithm, but why on earth would this algorithm ever come to a conclusion, right? Because you could imagine, and especially why would it terminate after a number of steps that depends only on epsilon and t? Like, that seems crazy, right? You could imagine you apply this algorithm to a graph, and maybe by the end, every vertex is in a separate part, and you have n parts, which would be kind of a sad conclusion, right? Because, that's not a very interesting kind of result, right? If I can if the number of parts is just n equal to the number of vertices, then I haven't really proven anything about graphs in some sense. So we want to say that this process terminates after a finite number of steps that only depends on epsilon and this other parameter t. But actually, really, it's only going to depend on epsilon. So the t was only used at the beginning to determine the initial number of parts. Yep. Well, that might look like what it's going on if you took any graph that you can draw and understand, because even if it had a million vertices, it might look like what you've done is you've just, the splitting up happened so fast that the parts ended up really small, and that was kind of the reason everything worked. But I mean, this is supposed to work for any size of graph. So in some sense, if the number of parts is a tower of height, some function of epsilon, but I have n vertices, and n can be anything, the parts actually aren't that small, and there's not that many parts compared to the number of vertices, because the number of vertices could be anything. It could be much larger than that. So this has to work. The amazing thing about this is this has to work for every graph. So in some sense, there might be something in what you're saying, but there's some kind of I don't want to call it magic because we're going to prove it. So it's not going to be magic in a little while. Yeah. So if n is massive, then you're never going to get parts that are even remotely small. They're all going to be massive parts. And still somehow this terminates after a number of steps depending only on epsilon. Okay. So maybe I'll just give some definitions and maybe talk about them a little bit, and then maybe we'll kind of use these definitions more next time. So essentially, if you want to show that this algorithm terminates, the way we're going to do this is kind of going to be, so we're going to define a function which sort of, in some weird way, it sort of is going to measure how good our partition is. Although the way it measures it is kind of almost indirect. But in some sense, it'll measure how well how good partition is in terms of epsilon regularity. And we'll show that as we do this refining process, this function increases by an amount that we can quantify. And we're going to show that this function can't go above 1 or something like that. And if this function keeps increasing by some quantifiable amount and it can't go past 1, then it must stop at some point, which depends on epsilon. So the function is going to be this related to this function f. So okay, so suppose I have disjoint non-empty sets A and B. I'm going to define FAB to be this. So take the number of edges from A to B, square it for whatever reason, and then again for whatever reason, divide it by n squared times the size of A times the size of B. Now, remember the density from A to B. So this has some of the same kind of common elements, right? So the density was the number of edges over A times B. This FAB is kind of like squaring the density, kind of. But the difference is this n squared on the bottom. So if I square the density, I just get this, right? So it's really just the same thing as the square of the density, except that one of the A times B's on the bottom gets replaced by n squared. Or so in other words, FAB is the same thing as the density squared times A times B over n squared. So now this gives us, this f function is going to give us a way of kind of measuring how good a partition is. So say we have a partition x1 up to xm of the vertex set. So we define the mean square density of P. So script P is it's the partitioning, to be f of script P, which is just the sum overall I not equal to j of f of xi xj, where the f thing is given here, right? Intuitively, the way we're going to think of it is that if f of P is large, then P is good. Good meaning in terms of like how epsilon regular it is. So we want to keep refining our partition and keep boosting this function f every time. So so here's kind of a description of why this algorithm terminates, which is going to kind of, so we're going to spend some time on this. So first of all, it's not hard to check that for any partition, f of P is at least 0 and at most 1. So the lower bound's trivial because all of, FAB is always non-negative, clearly. And then if you add up a bunch of non-negative numbers, it's non-negative. The upper bound is going to be, well, it's on your assignment 5. And when I was writing the notes and stuff, I wasn't too careful about this. So someone has already pointed out that you might be able to replace this with a 1/2. So still what I'm writing here is true, that it's at most 1, but it's also perhaps at most 1/2, but you don't have to prove that if you don't want to. So here's the amazing thing, is that if there's at least epsilon m squared bad, non-epsilon regular pairs, then our refining algorithm always increases f by at least, let's say, epsilon to the 5 over 2. So therefore, the algorithm must terminate because, f is at most 1. So it terminates after, at most, let's say, 2 over epsilon to the 5 steps. So here's a very valuable property which we're going to derive, is that if you refine a partition, this mean square density, which is the f value, so that's all I mean by mean square density, can't go down. And that's going to be a useful thing to do, because that means at any point, if we want to just take what we've got so far and just refine it a bit, we can know that we can do that without harming the f value. So you can refine kind of in arbitrary ways, and f of the partition doesn't go down. Just to be clear, so what is a refinement, right? The picture kind of says 1,000 words here, right? But, or however many words are in this definition, which is less than 1,000, I guess. But a refinement of a partition, like say if I partition to 3 sets, a refinement is just a partition that consists of just breaking up the sets of your previous partition into smaller sets, right? So if I took 3 sets and I then partitioned, in this way, this is not a refinement, because I'm, taking some of one set, some of another set. So a refinement is just like, where every set of the new partition is contained in one of the old partition. just to be clear about what I mean. Okay, so this is kind of going to be the key lemma for understanding how refinements affect the mean square density. So all we have to do is, to be honest, all we have to really do is think about a pair of sets, because remember the f value of the whole partition is just adding up overall pairs of the f value of that pair. So everything kind of does boil down to looking at a pair of sets. So let A and B be disjoint non-empty sets. And suppose we think of A, B as being a partition of some set of vertices. And now we want to refine it. So to refine it, we let A1 up to AT and B1 up to BS be partitions of A and B, respectively. So the picture is kind of like this. You've got two sets A and B, and I split A into T chunks and B into T chunks. Then what I claim is that if I want to compare the f value of A and B to the f value of the kind of pairs of chunks, what I get is that FAB is at most the sum I equals 1 to T, J equals 1 to S of F AI BJ. Okay. And the message here again is that this inequality goes in the kind of right way, right? That refining increases, or does not decrease, I should say, F. Where here, anyway, is that clear? Okay, so let's prove this. So here's a basic thing. So I mean, we have to deal with various things here, right? We've got we have to deal with the various parts of this F definition. So let me start with something which is fairly easy. So all I'm going to do is say how big is A times B, okay, in terms of my AIs and BIs. Well, the AIs partition A, so the size of A is just the sum I equals 1 to T of AI. The B's partition, the BJ's partition B, so I've got that. And the way multiplication works, right, with sums, distributing whatever, is that, you multiply everything here with everything here. So A times B is the same as the sum I equals 1 to T, J equals 1 to S, AI BJ. So nothing too deep there. So ignore this comment for a second. But so how would I count up the number of edges from A to B? And you get a sort of similar formula, because it's like, if I want to count edges from A to B, I can look over every pair of parts and just say, okay, I count up edges from A1 to B1, A1 to B2, and so on and so forth, A7 to B42, whatever. Just count over all the pairs and add up all the edges. So the number of edges from A to B is the same as summing up over all pairs of sets, I equals 1 to T, J equals 1 to S, edges from AI to B, J. So what happens if I do follow my own advice here and I divide this by A times B and I square it? Or maybe even if I just divide it by AB. So what do I get? I guess I get that divided by AB. But we have some notation for that. So, so EAB over A times B is this D thing. So if I divide by that and I square it, I get DAB squared equals the square of this sum over AB. Okay, so that's just rewriting what I wrote before. The thing is, one needs to sort of think of where are we and where do we need to get to. Neither of those things are really clear at this point, I don't think. But the thing is, we want to somehow compare my f of AB to all of the FAI BJs. It's sort of useful to then somehow introduce, this notation, this AI. So, so just by kind of playing with this definition of D, I get that, this EAI-BJ is just the density between AI and BJ times the sizes of them. Okay, so I just get something like this. We love this type of expression, right? We've done this kind of thing quite a lot, although this is going to be a little bit different. It's going to be a little bit trickier than some of the ones we've done, but sums of squares, right? this thing looks like, this thing has this kind of form. It's just a sum of something times something squared. Where, okay, I've got a double sum here, but you can think of the double sum as being a single sum, right? Over all pairs I and j. So, okay, so this is just one of these sums of squares things. The tricky part is kind of deciding what should be my xi and what should be my yi. If you do ponder about it for long enough, yeah, you can work it out. But let me tell you what it is. Yeah, it's hard to make this proof seem natural. But this is where we've gotten so far, okay? We've gotten to here. So what I'm going to do is I'm going to let xij, for each I and j, I let that be the square root of this thingy here. So this is just the square root of that. Oh, that's right. Yep, sorry. Thanks. That's good. It's probably going to come back on the next slide or something. But yeah, that's good. It should be squared. So all I'm doing is I'm going to apply this convexity inequality where I let xij be the square root of this thing. And then I let yij be everything that's left in this the term of this sum thing. So it's just like the density times the square root of that stuff, right? And if I multiply xi yj or xij yij, I get the thing that's inside here. Yeah, and then again I've got a missing square here, and right, so then I can apply this kind of convexity thing, and I get that. Yeah, so this is going to be, so for some reason the chat's not coming up when I click it, but hopefully it will pop up in a second. Right, so this is going to be the sum I equals 1 to t, j equals 1 to s. The nice thing about when I square xij is I get ai bj over ab. Okay, yeah. But if you kind of work backwards from what you want, you'll see in the end why this works, and then maybe it becomes a little bit nicer. So now what I get here is the sum over I and j, same limits on the sum, ai bj over ab times the density squared, I think. Yeah, that looks right. Okay, wait, what do I... So, okay. So what's the point here? So here, so remember I told you that a times b is equal to the sum, so double sum over I and j, ai bj. So that kind of gives me, I guess this just gives me 1, right? Because I can pull out the a times b on the bottom, and I sum everything up, and it just gives me a times b, so I just get 1. So what do I get here? I get, well, what I'm going to do is, so let's multiply everything. So here, this is not the thing I want to bound, right? I want to bound f. So to make it into f, I should take this whole thing and multiply it by a times b over n squared. And that'll give me f by this kind of formula thing. So sorry, this is n squared. Right. And what is this? So this is going to be, if I take the density here, I multiply it by ai times bj. That's kind of like f, except the n squared is missing. So this is kind of like f ai bj over, times n squared and over ab, I believe, right? If you plug in, if you kind of use this this thing and you solve for, let's say you solve for the density squared, plug that in, it gives you this, I think. Okay, so this is actually another way of writing what I had on the previous slide. Now I multiply both sides by a times b over n squared. So left hand side just becomes fab, because fab fab, maybe I should call it, is ab squared times ab over n squared. Yeah, because fab is the density squared times a times b over n squared. So if I multiply by this on both sides, that cancels, and then I'm left with fab at most, this sum, which is what I wanted. So again, the message is that if my goal is to make f large, refining a partition doesn't cause problems, because it can only increase the f value, which is cool, which is, I mean, it's very useful. So this is just a corollary of the previous lemma, So if I take any partitions, P and P prime, where P prime refines P, then, so what the lemma we just proved implies that the kind of coarser partition has a F value which is at most as large as the finer partition. So refining partitions increases the F value or doesn't decrease it. And so why does this follow from the lemma? And it's because you can just look at all pairs of sets. Like if I look at P, when I'm computing F just looks at pairs of sets, computes some value and adds them up. So actually really I can just kind of focus on a given pair of sets. And then in P prime, maybe each of these sets is refined. And then the kind of F value I get for P prime will just kind of, it'll replace F of X1, X2. Suppose I refined each of these into 4 sets with 16 different values, which is picking one set here and one set here. But what we've proven is that F of X1, X2 is at most the sum of those 16 values. So if you think of what gets replaced with what when you do the refinement in the definition of F, I think it's clear that this lemma is good enough to prove this. Yeah, so from that corollary, and really the work is being done by the lemma before it, what we've learned is that like any step of our algorithm can never decrease the mean square density, which is this F value. And that's good, right? Because I want to say that if we haven't found an epsilon regular partition, then we refine using this algorithm. And I want to say that the F value goes up. So what we've proven is that it doesn't go down, which is good. Not going down is like the first step to going up, right? But it's not good enough for us to just say it goes up. We need to kind of be able to quantify how much it goes up by. So I want to say that when I do this refinement, the F value goes up by an amount that I can measure. So that's going to come from the following lemma. So let A, B, and B be disjoint non-empty sets. Suppose that A1, A2 is a partition of A, and B1, B2 is a partition of B. Then, so what I'm saying here is that if I add up FA1, B1, A1, B2, A2, B1, A2, B2, I take these 4, think of splitting up A into 2 sets, B into 2 sets, right? If I add up all those 4 F values that you get, it's at least FAB plus this quantity, which now depends on the densities between the sets. So it's what we've got here is a D A1 B1 minus the density AB squared times the size of A1 times the size of B1. And the good thing about this being squared, when you square a number, right, if it's positive or negative, the square is positive, right? So what this is saying is that the density of A1 B1 differs substantially from the density of AB. Let's say it differs by epsilon, right? Then we're going to be able to say that this is at least epsilon, you get that this is at least epsilon squared. And if I know that A1 and B1 are not too small, suppose that this comes from doing this refinement procedure. So A1 is a subset of A, which has size at least epsilon times the size of A. Let's suppose that B1 is a subset of B. B1 is at least epsilon B, right? And let's suppose that their densities deviate by a lot, right? So that the density from A1 to A2 minus DAB absolute value is at least epsilon, right? So what this will tell us is that doing this refinement boosts the F value by, it gets boosted by at least epsilon squared times epsilon times times epsilon times A times another epsilon times B over n squared. So, which is epsilon to the 4 AB over n squared, right? And if I knew that so I'm thinking of all of this in terms of the algorithm. So let's think of just the first step of the algorithm. So I've taken my partition in sets of size T sets of size n over T. So I can think of my A as being roughly n over T vertices. So this is in the first step of the algorithm, but every step is going to be sort of the same, except T will be replaced by a different number. So then this is going to be at least epsilon to the 4 over T squared, roughly. So there's some floors and ceilings, but who cares about floors and ceilings? And now imagine if the number of bad pairs, like bad pair, so here I'm thinking of A and B as being a bad pair, a non-epsilon regular pair. If the number of non-epsilon regular pairs was at least epsilon t squared, and you have to do a bit of thinking to make sure that you win for all of them simultaneously. But suppose that the number of bad pairs, pairs that are not epsilon regular, is at least epsilon t squared, right? If it was less than that, I would have stopped the algorithm already. So then in total, because if you win this amount for every pair, in total you're going to win at least epsilon to the 5. Okay, so let's prove this lemma. So I'm going to start with something trivial. Okay, and this kind of addresses, there was a question at the end last time about, like, there's something weird here. This is not symmetric. This is like in terms of A1 and B1 and not A2, B2, A1, B1, or A1, B2, A2, B1. So what I'm going to do right from the beginning is actually I'm going to introduce these other things. So if I write this, so this is the numerator, or yeah, that's the numerator here, right? And this is, of course, at most as large as if I summed up over all pairs AI, Bj, and I computed the same kind of expression. And this is, why is this trivial? It's trivial because, I mean, there's more stuff here. And all the things I'm adding here are positive or non-negative because it's like the size of a set times the size of a set, which is non-negative, non-negative, times a square, which is non-negative. So this side is bigger. The stuff on this side of the inequality is bigger than the other side because it's just got more stuff, which is all non-negative. Okay, so now what I want to do is kind of try to simplify things. So I'm looking at like this sum, and I look at this square, and let's play around with that square by expanding it. So, okay, we know how to expand squares, right? You just take d of AI bj squared minus 2 times d of AI bj dab, and then you have dab squared. Okay, nothing, oops, I've written the squared twice. Okay, nothing complicated there. But now we can kind of expand out all of this, including, keeping this stuff. So I get 3 kind of sums, right? Where the first one I keep, the dai bj squared term, right? And then I have minus 2 times where I keep the thing is, like, AB doesn't depend on I and J, right? DAB, so that can be pulled outside in the front of the sum. And here I can pull DAB squared in front of the sum. Okay, so just at this point, it's all just algebra. But now I'm going to want to try to understand these 3 terms in some sense. So actually, I think these are in kind of decreasing order of complexity. So the last term, like this one is the easiest one to understand. So this is just A1 times B1, A1 times B2, A2 times B1, A2 times B2, which is just A times B. And of course, you've still got the density squared. Okay. If I go over to the next term over, it's actually also kind of simple, because what is the density AIBJ? Well, it's the number of edges over this thing. So they cancel, right? So here I'm just writing what the D function gives you. And of course, when I multiply it to this, it just cancels and it just counts edges from AI to BJ. And then when we sum up over all I and J, the number of edges from AI to BJ, the whole thing just gives us, so this whole sum just gives us the edges from A to B. Am I going too fast, or is this okay? Okay. And then the first term, that's not so bad either. So, well, if in terms of this f function, but maybe let's, yeah. So this is just repeating the 2 kind of easy things here, that this was just EAB, and this was just A times B, right? And so this is just kind of, I've just substituted the things that we calculated last time in for these terms. And actually, I can simplify this even further. Yeah, because what I've got written here, if I take DAB, times the edges from A to B, which is basically what I've got here, right? Times 2, or -2, whatever. That's the same thing as squaring the density and then multiplying by AB, because the density, of course, again, is just, it's just the number of edges over this product. So if I square that, I multiply it by AB, what I get is, the same as DAB, EAB. Right, so these last two terms are kind of the same, except that this one has a -2 in front of it. So they all combine together to just give me this. Right, let's just take this -2 and add 1 and whatever. So the kind of inequality that we've come to now, okay, so the inequality that we've proven, so where I started with this A1 times B1 times that. So now on this slide, I've just divided by n squared. So just to kind of verify that, that is where I started. If you see it here, A1 times B1 times the difference in the densities squared. And I proved it's at most, blah, 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 blah. And then where we got to was that it's at most this thing, except without the n squareds. But so now I'm just dividing everything by n squared. Okay, but this is what we've proven so far. And now we've actually just got a formula. I mean, we can just, everything that's sitting here is exactly my fxy, because FAI BJ and FAB, because for any sets x and y, fxy is just equal to this. So this was this thing that, you can kind of derive. So the way we actually defined fxy in the beginning was take the number of edges squared between them and divide by n squared xy, right? But that's the same as this. Okay, so now if you rearrange, you bring this thing to the other side, right? The other side is over here. Then what we've proven is exactly what we asked for. That if I take the the sum of all the density, or the f value, FAI BJ, I sum that up over all I and j. I is 1 or 2, j is 1 or 2. That's at least FAB plus this thing, which kind of measures how different the densities were between A1, B1, and AB. And so that completes the proof of that. Okay, this is going to be this is really the kind of workhorse in this theorem. This is doing all the work, right? This is how we're going to get a boost in our mean square density by doing this kind of refinement procedure. So now we have almost everything we need. So let me now give you the final proof of the regularity lemma. And the last thing we're going to have to do is deal with this issue of making the parts the same size. But everything else we've got we've kind of built up already. Okay, so here's the kind of the algorithm again, right? You start at the beginning by partitioning your vertices into sets, or into t sets, each of size, where xi 0 has size, roughly n over t. Okay, really I mean the floor or the ceiling of n over t. Now we kind of have so that's kind of the base construction. And now we kind of inductively keep refining the partition in the following way. So suppose we've done S steps so far. S could be 0. So it could be that we're dealing with the initial partition. And we've reached a partition P. So I'm going to call it script P S in the superscript S, which is x1 up to x sub k sub s superscript s, which is a bit of a mouthful, but So the number of parts here is ks. And I'm going to assume at this point that I've done my kind of reorganization so that all the parts have about the same size. So every part of the partition has size n over ks floor or n over ks ceiling. We'll see why that's quite useful. Right. So the algorithm says it looks over all the pairs and it says, okay, is it epsilon regular or not? And counts up all the pairs which are not epsilon regular. If the number of such pairs is less than k epsilon times the number of parts squared, so number of parts is ks, then stop. And we just output ps, and this is the partition which proves the theorem, right? This will this will be a good partition because less than epsilon ks squared pairs of parts are not epsilon regular. So of course, we should assume that our life is not that good, right? So we haven't gotten lucky. So there's a lot of pairs that are not epsilon regular. And what we do is we do this kind of greedy refinement procedure we've been talking about, where for every pair, we find a set. So if xi, xj, superscript s, is not epsilon regular, you can find a set in xi, I'm going to call it aij, and a set in a subset of xj, which I'll call aji. So I just switch the indices such that aij has a epsilon proportion of xi, aji has an epsilon proportion, at least an epsilon proportion of xj, and the difference in the densities is at least epsilon, right? That's my kind of certificate for non-epsilon regularity. And we just do this kind of Venn diagram thing where for every part of the partition of V of G, we break it up into kind of segments corresponding to the kind of Venn diagram generated by looking at all these certificates. Formally, this ends up being sets of the form. So xi gets broken up into things of the form, like where you have a subset of the indices that doesn't include I, and you have aij. Yeah, I think it's just better to think of the Venn diagram thing, right? Just, this is my certificate for one set, for one other xj being non-epsilon regular. So this is inside of xi. I've got another certificate. I've got another one which breaks all of these things into two pieces. I've got another one, and you just take the segments of those, of that Venn diagram. So that's my new partition, and I'm going to call it QS+1 because it's not really, I can't really kind of inductively do things yet because the partition classes are not the same size. So we're going to then, from QS+1, we're going to define a PS+1 that has the parts being the same size, roughly. But anyway, we can start with QS+1. Is it clear what's going on? So this is again, just the same algorithm again. Okay. So yeah, okay. This is a fact. We've kind of analyzed how these numbers work before. So the number of parts in this, so QS+1 is kind of clearly a refinement of PS. And the number of sets you get is like KS 2 to the KS minus 1, where the KS comes from the number of sets in P, right? Now we want to compare the mean square density of QS+1 to the mean square density of PS, and we want to show that it went up a lot. Where, okay, a lot is not going to look like a lot because it's going to just be epsilon to the 5 over 2 or something, which if epsilon's small, then that's a small number, but it's kind of a substantial increase in terms of in terms of the grand scheme of things, because f can never go above 1. Okay, to see that the mean square density went up by a lot, what you have to do is kind of think about, for each pair that's not epsilon regular, like if I look at the pair xi xj corresponds to one term in the kind of definition of PS, right? So when I compute f of PS, I get a term which is f of xi xj, where everything has an superscript of s. But yeah, I maybe won't say that every time. But the contribution of this is literally just that in PS. But in QS+1, the contribution kind of coming from the pair xi xj is the sum over all the subsets of xi that are in QS+1 and all the subsets of xj which are in QS+1 of f of ab. And these a's and b's are the sets you get from the kind of Venn diagram thing. So what happens if I compare f of PS to f of QS+1, what happened is I replaced each term like this with kind of oodles and oodles of terms like this, like, all of the terms of this sum. But that's all that happened, right? It's just kind of everywhere you saw, or you see one of these and you just replace it by this. And I want to say that this replacement, if xi xj was not epsilon regular, then that replacement kind of individually boosts the density by a certain amount. And then if we have lots of non-epsilon regular pairs, I do all of those replacements, and I want to say that it boosts even more. So what happens when I replace xi, xj by this? And I want to kind of think of that weirdly kind of in two steps. So I'm going to replace xi, xj to something else, and then replace that something else with this thing, and kind of measure how much it goes up. Right. Okay, actually, I'm going to go the other way around. So suppose I start by looking at the thing. So just focus on this sum right now. So this is the thing that xi, xj gets replaced with. It gets replaced with this entire sum. Now, I claim that this this sum is over a lot of sets, a lot of pairs of sets. But I claim that this is at least as big as if I just looked at this. So these four terms, but by the way, these four terms don't actually appear in that sum. These four terms are coming from, I look at my certificate for that pair, my certificate of non-epsilon regularity, and I just look at, this and the complement and all that. And the reason is that, so here I'm summing over a partition, some partition on this side, and here I'm summing over some partition where it's a much simpler partition. It's just into, each of these things get partitioned into two sets. And this one is finer. So this is a refinement. So this partition is a refinement of the partition where I take like x1 or aij, I mean xij minus aij, and then do a similar thing for, oh, sorry, that's not what that's called. It's not, there's no such thing as xij. I mean xi superscript s. And it's a refinement of that, and on the j side, it's a refinement of this partition here, where I just take aji and I take the complement. So by one of the lemmas we proved, I think last time, when you refine things, the f value goes up. So the mean square density here should be at least these four terms, because this is a coarser partition that we're dealing with here. But now if I look at these four terms, I can use the last lemma we proved to say that this is at least f of xi, xj plus some stuff. So this is just using the last lemma, because this is exactly the situation we had in the last lemma. We had two sets which are broken into two pieces each. And this was the bound you got. And now I can say that this is at least, okay, so if I'm assuming that it's not epsilon regular, I can say that the thingy inside of here, inside the square, is at least epsilon. The absolute value of it is at least epsilon. If I square it, it's at least epsilon squared. aij, what do I know about that? It's at least epsilon times xi, superscript s. And something similar here with xj. So I get times epsilon xi times epsilon xj. And here's the thing. I know how big xi and xj are. I mean, roughly. They're both about the same size, and they're both about n over the number of parts, which is ks. So this is basically giving me epsilon to the 4 over, so these n's cancel with this n, so you kind of have ks squared on the bottom. So let's kind of, yeah, so, right, so when I replace the xi and xj by this kind of Venn diagram thing, what it does to the mean square density is it replaces this term by something which is at least as big as it was before, plus this. Where here I'm just taking floor for both of them because I'm doing a lower bound. And then just to be wasteful, I don't really care about factors of 2, so I don't like floors. So I can say this is at least, let's say, I don't know, epsilon to the 4 over 2 ks squared. That's just getting rid of the floor and wasting a factor of 2, but who cares? But now remember, I had this assumption that my partition wasn't good, which means that the number of bad pairs is at least epsilon ks squared. So I had at least this many non-epsilon regular pairs. And for every single one of them, the term in the sum corresponding to them gets replaced by something which is at least this much bigger. So I get kind of, okay, here I guess I've got epsilon, I've kind of gone back to this step, I guess, but then times epsilon ks squared, imagine I put this into here, ks squareds cancel, and I get epsilon to the 5 over 2 overall. So overall, my mean square density is boosted by epsilon to the 5 over 2, which tells you that this thing can't go on forever because the mean square density is always at most 1 or at most 1/2 or whatever it is. So this can't go on forever, so it must halt after a certain number of steps, which is maybe 2 over epsilon to the 5 or something. But here's the thing. So I haven't made the parts the same size. That is the sticking. So the last thing to do is to get the parts to be the same size. So here's what I'm going to do. So, okay, so I know how many parts, okay, I don't know how many parts QS plus 1 has. So QS plus 1 is the thing we got by breaking into Venn diagrams and whatever. It has at most this many parts. What I'm going to do is I'm going to make the number of parts a heck of a lot larger. So I'm going to take this upper bound I had here, I'm going to multiply it by 8. Okay, that's not too important. And then divide it by epsilon to the 5. And this is the number of parts that my PS plus 1 will have. So this is the number of parts we are going to aim for in PS plus 1. Okay, so basically, if you think about it, it's kind of like every part of QS plus 1 is going to be turned into like 8 over epsilon to the 5 parts. Although, remember, like the parts of QS plus 1 might be really tiny. Like I might have parts of size 1 in QS plus 1 because that just might be how big the segment of the Venn diagram was. So I can't just split up my parts of QS plus 1 finer because some of them might be really tiny. I'm going to need to kind of incorporate those tiny ones into bigger parts. And at the same time, I'm going to take my big parts and make them smaller. So let's see how that works. So take my partition that I've got so far, my QS plus 1. It breaks the vertices into classes and just write them in a linear order from left to right. So I've got a class here, I've got another class. And actually, like you could have, so this, possibly you could have a really tiny class somewhere and whatever. So these blobs kind of look the same size, but that's, they're not necessarily the same size. And what I'm going to do is I'm going to refine QS plus 1. I'm going to call it QS plus 1 tilde. And I'm just going to take a bunch of intervals in this order where the interval size is either n over k sub s plus 1. So that's my number here that I defined on the previous slide, this thing. So that's the size of parts we're aiming for, right? So it's either going to be the floor or the ceiling of that value. And we just do it in some way that so that the number which are equal to the floor is equal, the right number. So just start maybe with floors or ceilings or whatever, and just, make the number theory work out, if that makes sense. Now, here's the thing. If I refine QS plus 1, with these intervals, so I take my first part, it's going to have an interval here, and then another interval. It's going to have about epsilon to the 5, it's going to have about 8 over epsilon to the 5 intervals in it or something, or more than that, actually, potentially. But things go a bit wrong on the boundaries, right? So I think of this being 2 sets on the boundaries, right? This, and also if I take a set that's tiny, maybe it's even smaller than my interval length. I kind of consider this basically I take the common refinement with the intervals and QS plus 1. So, but if you think about it, a vast majority of the parts are going to be the right size. They're going to be, this size or that size because these intervals are so short. But you're going to have some which are coming from the boundaries of these intervals, from the boundaries of the classes, which are small. Okay, and here's the thing: QS plus 1 is at least QS plus 1 tilde, the common refinement of the intervals and the parts that we had before, is at least as good as QS plus 1 in terms of the mean square density, because it's a common refinement of 2 things. It's a refinement of QS plus 1. So the mean square density of QS plus 1 tilde is at least as large as that of QS plus 1. And a vast majority of the sets in QS plus 1 have the right size. Actually, if you think about how many don't have the right size, and I think it's at most as many sets as Q had, right? Because the only time you get sets which are the wrong size is when they're actually touching the boundary of 2 sets. So, and the number of kind of boundaries here is like how many sets were in QS, or QS plus 1, minus 1 or something. Okay, and each of those corresponds to possibly 2 bad sets or something. So like the number of small sets you have, which are not the right size, is kind of small. And here's how we come up with our partition, our s plus 1th partition. So we take this qs plus 1 tilde, which has practically all the parts being the same size, except for these little kind of bad parts. We just take all the bad stuff and throw it in its own little box and then split it up arbitrarily. So we don't even care what happens with that stuff. We split it into sets of these sizes. Now we have to show that, okay, the mean square density didn't go down too much. So what did we lose by doing this? Right. Yeah, so here I'm kind of computing, let's say EXI, XJ. Maybe I'll call them, oh, I don't know what to call them, but I'm computing my F value, this squared over n squared xi xj. Sorry, not xi xj. Oh yeah, okay. Where xi is one of the parts made up from the garbage stuff. The garbage being those bad intervals, and xj is any other part. Well, I'm kind of computing an upper bound on this, so I'm just writing. Yeah, it's a bit perhaps hard to kind of parse this, but okay, we are kind of out of time. But if you think about this, by putting all this garbage stuff together and breaking it up arbitrarily, the amount of mean square density you've lost is at most epsilon 5 over 8. And this comes from the fact that I picked ks plus 1 to be, at least as large as the number of parts in qs plus 1 times 8 over epsilon to the 5. So that's where these numbers come from. So the final story is that, the final kind of conclusion is that ps plus 1 has mean square density at least that of ps, or yeah, p to the s, and then plus epsilon to 5 over 2 minus what we lose from making the parts the same size, which was epsilon 5 to the 5 over 8. So it went up by a positive kind of measurable amount. And that completes the proof.